Here's an example of arc length on a parameterized curve. So our assignment is to find the arc length around a circle of radius r. So here's your radius r circle. You start here. Maybe you start here. You could parameterize it anyway. But I'm going to start here at r comma 0 and go around the circle like that and find that arc length. So a parameterization of that circle will be x of t is r cosine t, y of t is r sine t, 0 to 2 pi is what the parameter clicks off. So let's just check it, make sure it really covers what it's supposed to cover. So when t equals 0, you're going to be at x equals r times cosine of 0 is 1. You're going to be at r. That's good so far. And when t is 0, this is 0, so you're going to be at r comma 0, which is checking off right. And I think we could believe that if you checked out t equal pi, for example, and put it in there, it'd be negative r, and that'd be 0. So negative r, 0. So it's working, and then it finishes up at 2 pi. So to go find the arc length, x prime is negative r sine t, because derivative of cosine is negative sine, and derivative of sine is cosine. So here's your derivative and your velocity function actually. Then your arc length is going to formula is right here. And so you're just going to plug everything in. 0 to 2 pi. You plug the x prime and the y prime in. Square that out, you get this. You can see it coming. The r squared is factored out, and the square root of r squared is r on the outside. What's left in there is sine squared t plus cosine squared t, which is 1. And the square root of 1 is 1. So then factor out the r outside of the integral. You get this. Evaluate it. And the antiderivative for 1 is t. Evaluating from 0 to 2 pi. And it's this. And of course you get 2 pi r, which is indeed the circumference of a circle of radius r.